I believe previously we'd been looking at factors affecting the effectiveness of preservatives, okay? And we looked at different factors that would actually affect, or rather, the availability of a preservative, okay? So if you look back, think of interaction with formulation components. We talked about a preservative being able to interact with the components in the product. We looked at, and remember we said your preservative is not active unless it is free. So if it is interacting with formulation components, it means that the preservative effectiveness will go down. We looked at the effect of pH. Remember we said it is only the undissociated preservative that is effective. So if you buffer your product at a pH where the preservative is dissociated, then it will not be effective. We looked at efficiency in multi-phase systems, okay? And we talked about the possibility that your preservative could be partitioned in the oil phase, in the micelles, okay, in polymeric suspending agents. Again, it could get adsorbed, okay. Again, remember, the key principle here is that for preservative to be effective, it must be free. So if it is not free, it means that you do not have active preservative, okay. Then we also looked at effect of container or packaging, and we said that your container or packaging will actually, it's possible for your preservative to adsorb onto the container, and if it actually does adsorb, it means that you will not have free preservative, and you will not get the effective concentrations required. Yes, so those are some of the factors we looked at that would affect your effectiveness. Then last week we looked at different preservatives, the characteristics of preservatives, okay? And we looked at what are some of the performance requirements, okay? For instance, you need antimicrobial activity. Don't just add a preservative to a pharmaceutical product and yet it's not effective. So for instance, if you're telling us, remember the scenario we talked about with the eye? We said that if you're adding, one of the requirements when you're adding a preservative to an eye product is that the preservative should be effective against Pseudomonas aeruginosa. Why is that? Because this is microorganisms that can be found on the skin, and it's possible that the patient can actually introduce it into the pharmaceutical product. What is wrong with this specific microorganism? Number one, it is very virulent. It causes disease very fast in the eye, okay? And it is very hard to treat. So we don't want a scenario whereby we have a pharmaceutical product that has this microorganism in it. So any preservative we add to eye drops must actually be effective against Pseudomonas, and that is a similar scenario we're talking about here, okay? Antimicrobial activity. You need to be able to prove antimicrobial activity before you add preservative, because remember the scenario we talked about, you're not adding preservative just for the sake of it, okay? You want to reduce interactions, so you only use excipients that are very necessary, okay? We talked about aqueous solubility. Remember the case we talked about with regards to oil emulsions or rather emulsions, okay? Where if you get the preservative getting sequestered in the oil, then it means that your product is not preserved because microorganisms will go into the aqueous phase. We talked about partitioning behavior, stability properties, non-irritant properties. These are all properties that you need to actually think about when looking at the performance of a preservative. Organoleptic properties, if you're going to use a preservative in the ear, or rather in the nose, okay, in the eyes, okay, in the oral cavity, these are preservatives where you want to think about organoleptic properties, okay? For those of you who have put, you know, substances in the, it's possible for you to put something in the nose. You can smell it, you can taste it, okay? Even from the eye, okay? Is it possible for you to get that taste from something in the eye? Amina, okay. Why is that?
Um, because of the nasolacrimal drainage.
Okay. Yes. So again, anything that, remember, in this case, we are looking at characteristics that can actually be tested, smelled, and all that. You want them to be very comfortable for your patient. So again, that is why we are looking at all this. And then last but not least, compatibility. We looked at that. We looked at the ideal preservative. Okay. What are the characteristics of your ideal preservative? Then we looked at regulatory expectations for preservative. So there should be a reason for inclusion. Don't just add to mask your inadequacies. There should be proof of efficacy. There should be safety information on the preservative. There should be control methods in finished products and details of labeling. You must indicate that this product contains ABC, so that if you have a patient who is allergic to that preservative, they know not to use that product. Okay. But if they get harmed and yet you did not indicate the kind of preservative available there, then they can sue you. So those are the regulatory expectations for preservative. And I believe that's where we stopped last week. So today we'll be looking at some of the preservatives that are available out there. Of course, the list is not exhaustive, but this is just to give you an idea of what's available, okay, and how they work, okay. So we have acids, for example, benzoic acid, sorbic acid, boric acid. We have esters such as the parabens, okay. These are the methyl paraben, ethyl paraben, okay. Those are some of the examples. Then we have alcohols, chlorobutanol, benzyl alcohol. We have phenols, such as phenol itself, chlorocreso, phenyl, phenol, okay. We have mercurial compounds such as thiomersal, nitromersal, okay. We have quaternary ammonium compounds such as benzalkonium chloride, cetyl pyridinium chloride, okay. So where do these antimicrobials work? Okay, these preservatives, where do they work? So the site of preservative activity in the microbial cell, one, a chemical has to undergo a sequence of events for it to be able to exhibit antimicrobial activity. Okay, first, the chemical will start with adsorbing onto the cell surface, and then if the compound has intracellular site of action, adsorption is followed by passage through either porine channels in gram-negative cells or diffusion across into the lipid-rich cytoplasmic membrane. But remember, the microorganisms might as the chemical might as well also work on the microbial cell wall or cell membrane. Okay, so this is followed by interaction with proteins, enzymes, nucleic acids, or other targets within the cell. And these processes are influenced by the physicochemical characteristics of the antimicrobial. For instance, ionization constant, lipid solubility. Okay, this will basically influence, where the chemical will be able to get to within the cell. Then antimicrobial activity is influenced by the affinity of the antimicrobial agent for structural or molecular components of the cell. So, for instance, you may get a preservative that has a high affinity, say for DNA, okay, or it may have a high affinity for the cytoplasmic membrane, or it may have a higher affinity for some specific proteins within the cell. That's what we are talking about. So there are certain molecular features of antimicrobials that are associated with activity against particular cellular targets. Activity may depend upon the attraction of dissimilar charges or on hydrophobic interactions. Okay, antimicrobials whose active species is positively charged, for example, the quaternary ammonium compounds and chlorhexidine, will display an affinity for negatively charged sugar residues on microbial cell surface or phosphate groups on membranes. So again, we're just basically trying to explain the fact that antimicrobials will tend to have an attraction for specific species within the cell, okay? And then they will disrupt those species. Absorption of these antimicrobials and consequently their activity increases as the pH increases and the cell surface becomes more electronegative. So, for instance, looking at this table, you can see different antimicrobials will have affinity for different areas within the cell. Okay, so we have those ones that have an affinity for the cell wall. Think of phenols, aryl alkyl acids, organomercurials, EDTA, chlorhexidine, okay, those will have an affinity for the cell wall, and meaning that they will actually act on the cell wall to disrupt the activity within the cell. Then we have cytoplasmic membrane, okay, where we have things like 2-phenoxyethanol, parabens, organomercurials, again EDTA, okay, those will have activity against the cytoplasmic membrane. Again, when you think about the cytoplasmic membrane, once you disrupt the membrane, think of the function of the membrane. Think of the function of the cell wall, okay? So it means that if you disrupt this cell wall and yet it is performing a function, it means that that function is interfered with. If the purpose of the cytoplasmic membrane is to enclose the contents of the cell, okay, it means that if you disrupt the cytoplasmic membrane, what is going to happen to the contents within the cell? The cell will release them into the environment. And of course, if that happens, the cell will be compromised and die, okay? So those are some of the things that will happen. Think of the functions of the cell wall, okay? If you disrupt the cell wall, what will happen, okay? Then it means that the cell will also be able to take in too much water and break, again compromising the cell, okay? So think of the cytoplasm. We have things like aryl alkyl acids, halogenated preservatives, okay? Chlorhexidine in high concentrations will affect the cytoplasm. So again, I believe one of the things we said last week was some antimicrobials will work on a different site at low concentrations, but when you increase the concentration, you are basically able to affect other parts within the cell. So for instance, think of chlorhexidine. In high concentration, it is able to get into the cytoplasm and cause disruption. Okay. So how do these antimicrobials work? Okay, let's look at some of the modes of action of these antimicrobials. So starting with weak organic acids, these are active against bacteria and fungi. In solution, weak acid preservatives will exist in pH-dependent equilibrium between undissociated and dissociated, okay? So we have the ionized and then we have the non-ionized, depending on the pH of the media, okay? So they have optimal inhibitory activity at low pH, since this favors the uncharged and dissociated state of the molecule. This undissociated state is freely permeable across the plasma membrane and thus able to enter the cell. Okay. On encountering the higher pH within the cell, the molecule will dissociate, resulting in release of charged anions and protons. The charged anions and protons are trapped inside the cell and cannot cross the plasma membrane. So what we are saying is you get at low pH, this organic acids are undissociated, okay? They are non-ionized. Because of this non-ionized form, they are able to easily cross the membrane. But when they get into the cell, because the pH within the cell is higher, they become ionized. Now, the problem is when they ionize, they become trapped within the cell, so they cannot cross the plasma membrane. What happens when they become trapped in there? Okay, they'll cause membrane disruption, inhibition of essential metabolic reactions, stress on the intracellular pH homeostasis, and accumulation of toxic anions. So with all this, they are able to disrupt the cell and then cause the death of the cell. Okay. Then for antimicrobials with long alkyl chains, so you may have acids, but in addition to them being organic acids, they have long alkyl chains, okay? These chains may integrate into the hydrophobic region of the phospholipid bilayer within the membrane. And what happens after this? It causes disruption of the membrane, leading to fetal permeability changes. And with fetal permeability changes, we just mean the membrane is distorted. Remember, these alkyl chains have integrated into the hydrophobic region of the phospholipid layer. Remember what we said. What is the function of the phospholipid bilayer? It basically controls what enters and leaves the cell. But now if you destroy this bilayer, what will happen? There will be no control to what is able to enter or leave the cell. Okay, so and usually these changes are fatal. It basically kills the cells. Okay, so that's it for the acids. Next, we have the aldehyde. Okay, for example, glutaraldehyde, they are electrophiles, hence are able to react with molecules possessing the thiol or AH groups or amino groups such as proteins. This reaction increases with pH, therefore aldehydes are more active in alkaline conditions. Okay. Then we have heavy metals containing antimicrobials, for example, the phenyl mercury. This will inactivate enzymes and structural proteins due to interaction with the thiol groups on the enzymes. Their use has declined over the years due to possibilities of mercury poisoning. Then we have the phenols and bisphenols, okay? They incorporate a hydroxyl group that is capable of generating a labile proton, thus acting as weak acids, okay? Their weakly acidic nature combined with significant lipid solubility are properties associated with uncoupling agents. They can disrupt the proton motive force that is responsible for oxidative phosphorylation in the cell. Remember, with oxidative phosphorylation, what are you looking at? You're looking at energy generation. But now, if you're able to disrupt this process, it means that the cell is no longer able to generate energy. Okay? It is thought that these molecules dissolve in the lipid bilayer of the membrane and act as proton conductors by virtue of their ionizability. This results in failure of many important energy required processes in the cell, including concentration and retention of sugars and amino acids. So again, if you're going to disrupt the oxidative phosphorylation, which is responsible for generation of energy, then what is going to happen? Any activity within the cell requiring energy will not be able to happen. Okay? Then we have biguanides. This may induce phase separation, leading to the formation of domains within the phospholipid bilayer. Okay? Chlorhexidine inhibits membrane ATPase, thereby inhibiting cellular anaerobic activity. At higher concentrations, it induces precipitation of cytoplasmic nucleic acids and related proteins. So again, this is similar to what we were saying, that at low activity, okay, it will inhibit membrane ATPase. At higher concentration, it leads to precipitation of cytoplasmic nucleic acids. Okay, then we have chelators such as edetic acid EDTA. This will compromise integrity of the cytoplasmic membrane by chelating calcium and magnesium. So you can imagine these ions are supposed to be available for the cell, okay? And they are there for a purpose. But now when you get EDTA, which is going in and chelating out these ions, okay? What happens is that these processes where these ions are required will be affected, okay? So this makes these ions unavailable to the microbial cell and potentiates the action of other antimicrobial agents such as 4-chloroxylenol and weak acid preservatives. So again, you remember the synergistic activity, okay? Whereby now if the chelators weaken the microorganisms, it means that the other preservatives will be able to kill the microorganism very fast, okay? Then we have the quaternary ammonium compounds. They display an affinity for negative charges of the sugar residues on microbial cell surface or phosphate groups on membranes. Okay, this will bind strongly to the cytoplasmic membrane, leading to general cytoplasmic membrane damage and subsequent leakage. So again, remember what we said. If the membrane is supposed to uh, control what enters and what leaves the cell, if you harm the membrane, then it means that you will have, like in this case, you're getting leakage because, it's the membrane is no longer functioning as it should. So this will particularly target the phospholipid bilayer. Okay? So what are the effects of preservatives on microbes? Okay, we've talked about where these preservatives will function. Okay, uh, which part of their modes of action. We've talked about some of them working on, chelating ions, others working on the cytoplasm, others working on, you know, uh, the membranes, phospholipid bilayers, okay? But now I want us to look at what is the effect of this action, okay? When they work on the cell wall, okay? What happens? This may lead to lysis due to enzyme inhibition. For example, in phenols and organomercurials, it can also involve irreversible cross-linking at the cell wall, for example, in glutaraldehyde, okay? Again, remember what we said. With all this, think about what function does the cell wall play. So if you interfere with the cell wall, what happens? Okay. Then we have cytoplasmic membrane activity. This may be due to effects on membrane potential, membrane enzymatic function, or general membrane permeability. So remember from your physiology, membrane potential is very important uh, with regards to how the cell functions. Okay, those membrane potentials are important. They will control opening of pores. They will control the integrity of the membrane and all that. But now, if you interfere with that, it means that the general function of the membrane will be interfered with, okay? Cetrimide, chlorhexidine, all those will affect membrane permeability, which allows leaking of essential cell nutrients, leading to cell death. Then we have sorbic acid inhibitants, or rather, sorbic acid will inhibit transport mechanisms across the cytoplasmic membrane and suppress fumarate oxidation. So again, remember, if you're inhibiting transport across the membrane, it means that you will, if there are essential items that need to go into the cell, then that means that the cell will actually suffer. Again, we talked about oxidation. Here you are looking at generating energy. But if you hinder generation of energy, what happens? You interfere with cell functions. Then cytoplasmic activity. This may involve uncoupling of oxidative and phosphorylation processes or interference with active transport mechanism, as is the case with weak carboxylic acid and alcoholic preservatives. So again, remember we said if you interfere with energy generation, it means that all activities requiring energy will fail. Okay. Other preservatives can inhibit electron transport chains, thereby inhibiting metabolic activity in an aerobic bacteria. Okay. Again, remember, if you inhibit electron transport, you may end up with accumulation of free radicals. Okay. And when these free radicals accumulate, it means that they will cause disruption within the cell. Then we have benzoic acid and parabens. This will inhibit folic acid synthesis. We have things like bronopol and other organomercurials, which target thiol enzymes in the cytoplasm. And then we have formaldehyde donators, such as imidurea, which act on the carboxylic and amino enzymes in the cytoplasm. Phenols and alcohols will cause protein denaturation. Okay. Any questions? Okay. So if there are no questions, we'll move to something else. I want us to look at testing of preservative effectiveness. Okay. How do we test the effectiveness of a preservative? Because remember, we don't want a scenario whereby we're just adding a preservative into a pharmaceutical product and we cannot prove that it is actually preventing the growth of microorganisms. Remember what we talked about with regards to eye products, okay? You want to be able to prove that the product that you're coming up to be used in the eye is not going to cause harm to the eye, okay? And if you're adding preservative, you need to be able to prove to us that that preservative is actually effective. But we said, remember we said it's not only effective, it is effective against specific microorganisms that we know are most likely to contaminate an eye drop if the patient is not very careful. And should they contaminate the eye drop, they are very virulent and hard to treat. Okay. So again, these are things that you need to be aware of. When you're talking about preservative effectiveness testing, there are specific microorganisms that we like to use for testing. Okay. So that we are sure that if this microorganism can be killed, then we are sure that others may not be able to survive. So antimicrobial preservatives, remember we said they are substances added to aqueous pharmaceutical products to protect them from microbiological growth or from microorganisms that are introduced inadvertently during or subsequent to the manufacturing process. So remember, we are not adding preservative to take care of our inadequacies during manufacturing, okay? Because that would be wrong. But if you have an aqueous product, then remember it is more likely to support growth of microorganisms. So you have to ensure that you actually take care of that. Non-sterile dosage forms may have preservatives added to protect them from growth of microorganisms inadvertently introduced during or subsequent to the manufacturing process. Antimicrobial preservatives are added to sterile articles packaged in multiple dose containers to inhibit growth of microorganisms that may be introduced from repeated withdrawal of individual doses. Okay, one or more antimicrobial preservatives are added to all sterile multi-dose units. So again, remember, with multi-dose units, it's possible that during withdrawal, you may introduce microorganisms. So for these ones, you need to add preservative. Antimicrobial preservatives should not be used as a substitute for good manufacturing practice. Remember, we've okay, and it should be below a level that may be toxic to human beings based on the recommended dosage of the medicinal product. So again, remember, these are chemicals, okay? We don't want a scenario whereby you're killing microorganisms, but again, you end up killing even uh, the patient, okay? Because these are chemicals. Sawa sawa. So that's what we are saying here, that within your final packaged product, you should be able to prove that the preservative is effective in the sense that it is killing microorganism, but you should also be able to prove that at that concentration, it is not causing harm to the patient. Okay? I hope that is clear. The concentration of an added antimicrobial preservative can be kept to a minimum if the active ingredient of the formulation process, or rather, the concentration of an added antimicrobial preservative can be kept to a minimum, okay? If the active ingredients of the formulation possess an intrinsic antimicrobial activity. And again, one of the things that you realize, if your API has antimicrobial activity in itself, then there is no need to actually add preservative to your pharmaceutical product because the API itself will stop growth of microorganisms. Okay? Remember, we said we don't want unnecessary excipients. Okay? Pharmaceutical preparations with adequate innate antimicrobial activity may not require addition of antimicrobial preservative. Aqueous preparations particularly require addition of preservatives to prevent proliferation or to limit microbial contamination during normal conditions of storage and use. Again, remember, these are normal conditions, not scenarios whereby your product has been stored so poorly, okay? Basically, we want to ensure that we are not, we are following GMP. Multi-dose containers uh, multi-dose containers could get contaminated during normal use and handling and present a hazard to the patient from infection and spoilage of the preparation. So again, that's why we add preservative to multi-dose. Antimicrobial preservatives must not be used as a substitute for good manufacturing practice. Again, we can't stress that hard enough. We have talked about that. The efficacy of an antimicrobial preservative may be enhanced or diminished by the active constituent of the preparation, or by the formulation in which it is incorporated, or by the container enclosure system. Okay, so again, remember we talked about factors that may affect activity of your preservative. Okay, so it's possible for you to have a well-balanced product. Okay, you have formulated it, you have balanced the preservative in it. Okay, question: does a liquid dosage form like amoxicillin contain preservative, considering its APIs and antimicrobial? This is actually what we are talking about. Most of the antibiotics, you can look at the antibiotics online. Most of them actually will not have preservative, okay? Because understanding is that the preservative itself, or rather, not preservative, the API itself, okay, will actually prevent growth of microorganisms, okay? So that's why you will find for most of these, they actually will not contain a preservative, okay? So I hope that is taken care of. But you can look at, if you have access to some of these products on the market, you can look at them, okay, and find out. When we talk about exceptions, okay, what are we looking at? Think of in what scenario, like the eye products that we are talking about, okay? What are some of the infections you would find being in the eye? Okay, we have microorganisms that may actually cause infection in the eye. Okay, is it possible that that microorganism that is causing infection in the eye, the antimicrobial that you are using to take care of that, okay, is not effective against Pseudomonas? Okay, then what do you do? Expectation is that you must protect against Pseudomonas. So what do? You add a preservative that is able to protect against Pseudomonas. Okay, so I hope that is clear. Okay, so we were talking about uh, anyway, let's pick up from the antimicrobial activity of the preparation in its final container is investigated over the period of validity to ensure that such activity has not been impaired by storage. So for instance, you add a preservative to a pharmaceutical product, okay? Expectation is that this product is well balanced, it is able to stay active for the period of the shelf life, okay? But you need to be able to prove that. How do you prove that? You test, okay? You test to see whether this preservative is actually effective. Because what did we say? We said that it's possible for you to add a preservative, calculate the right amount, but the preservative goes and absorbs on the container, okay? It absorbs onto the surfaces of the container. And what happens? It means that you will not have enough preservative within your product. So it's important for you to test and see the added preservative. Is it effective? Again, it's possible for you to add the right amount of preservative, but you have an emulsion. Instead of the preservative going into the water phase, it goes into the oil phase. What will happen? You will have proliferation of microorganisms in the aqueous phase. So you need to think about that. Sawa sawa. You may have a suspension. Instead of preservative remaining free, it attaches onto the solid particles. Then what happens? If that happens, you don't have free preservative. Remember, we've kept on saying for your preservative to be effective, it must be free. If it is not free, what will happen? You will have growth of microorganisms within your product. Okay, so such investigations may be carried out on samples removed from the final container immediately prior to testing. Okay, during development of a pharmaceutical preparation, it should be demonstrated that the antimicrobial activity of the preparation provides adequate protection from microbial contamination or proliferation during storage and use of the preparation. The efficacy of the antimicrobial activity may be demonstrated by the preservative effectiveness test. So, what are some of the, or rather, when you're testing preservative into different categories. Okay, we have category 1, 2, and 3. Category 1, for the purposes of testing preservative effectiveness, is composed of injections, okay, other parenterals including emulsions, otic products, sterile nasal products, ophthalmic products, okay, uh, products or and products made with aqueous bases or vehicles, okay. Then we have category 2, topically used products made with aqueous bases or vehicles, non-sterile nasal products, and emulsions, including those applied to mucous membranes. Then category 3, we have oral products other than antacids made with aqueous bases or vehicles. And category 4, which is composed of the antacids made with aqueous bases or vehicles. Okay. So, what are some of the test microorganisms? Remember, when we were looking at microorganisms of interest or of use that are useful for us in the pharmaceutical industry, okay? We talked about, for instance, when you're testing moist heat sterilization, you want a microorganism that is very hardy, that is very resistant to heat, so that if you expose these microorganisms to heat conditions and you're able to kill it, then you're sure every other microorganism around it is dead, okay? Because this microorganism has been known to be hardy, and therefore, if you kill it, then most likely the rest have actually been killed. Okay, so it's the same thing here. We are also there are specific microorganisms that have been chosen to be used for testing effectiveness of these preservatives. Okay, so some of these test microorganisms include Pseudomonas aeruginosa, that is just an identity code. Okay, then we have Staphylococcus aureus, Candida albicans, Aspergillus brasiliensis, and Escherichia coli. Okay, so test for efficacy of antimicrobial preservation. Single strain challenges are used, and the designated microorganisms are supplemented where appropriate by other strains or species that may represent likely contaminants to the preparation. So, for instance, uh, with this case, okay, E. coli, okay, is used for all oral preparations, okay. Zygosaccharomyces ruxi for oral preparations containing high concentrations of sugar, okay. So those are just some examples. The test should be conducted with a suitable volume of product. It is advisable to begin with at least 20 ml of product. The original product container should be used whenever possible. But remember, we are saying 20 ml of the product. Some of the products are even less than an ml. Okay, so remember, sometimes you may not always be able to achieve the ideal, okay, but if you're able to achieve it such that you can uh, test your product within the original container and use 20 ml of the volume of the product, again, that is well and good. But if you're not able to achieve that, then again, you need to, that's a compromise that you will reach, okay? You may need to combine a number of the product or into a bigger container and test. Of course, that is not the ideal, okay? But if you have a product that is less than ml, okay, then there's nothing you can do about it. You still have to test for efficacy, but uh, Again, I mean, you try to work with the conditions that are available, or you create the right conditions. So the original product container should be used whenever possible. If the amount of product in the container is much less than 20 ml, then a suitable volume of product can be transferred from individual original containers into 5 sterile capped bacteriological containers of suitable size. Okay. Note that during recovery, if the diluted product exhibits antimicrobial properties, specific neutralizers may need to be incorporated into the diluents or the recovery media to allow growth and recovery of the viable microorganisms. Okay. So let's look at the test. Okay. The product is separated out into 5 containers, each being challenged with one of the 5 method specified microorganisms at a concentration of 1 uh, times 10 to the power of 5 colony forming units per gram or per ml. Okay. We talked about Staph aureus, E. coli, Pseudomonas aeruginosa, Candida albicans. Okay. So all those, the 5 that we mentioned, okay, Aspergillus brasiliensis, all that are put into individual containers. The initial concentration of each microorganism is determined by inoculating a controlled substance and using standard dilution and plating techniques. The inoculated product is held at room temperature for a period of not less than 28 days. The product is evaluated at specific intervals within the 28-day period. Evaluation intervals depend on the category of the product specified by the method. At each contact time, the inoculated product is chemically neutralized and plated using standard dilution and plating techniques. So remember, you've taken your pharmaceutical product, you have added these microorganisms to that product, and then you let them incubate them for uh, 28 days. Okay. Then you come and check at intervals. Okay. You withdraw the product, you plate it. Okay. Uh, you neutralize, you withdraw the product, you neutralize the preservative that is in, and then you plate it and observe for growth of microorganisms. Of course, if the preservative is effective, you do not want to see growth. Okay. After 48 hours of incubation, surviving microorganisms are counted, and the log reduction for each microorganism at each interval is reported. Okay. The effectiveness of the preservative system is determined based on the passing criteria. So, for instance, this is the acceptance criteria for parenteral preparations, eye preparations, intrauterine preparations. These are basically things that are supposed to be sterile. Okay. So after that incubation, okay, remember we started with our pharmaceutical product that is preserved. Okay. Then we added the inoculated it with microorganisms. Okay. We come and observe at uh, 6 hours. Okay. Did we remember we are withdrawing and then plating to see whether there is growth? At 24 hours, we withdraw and plate to see whether there is growth. At 7 days, we withdraw and plate to see whether there is growth. Similarly to 14 days, 28 days. Okay. And this is what is expected. Okay. At 6 hours, you should have 2 log reduction. Okay. 100 times reduction in the number of microorganisms. Okay. Then at 24 hours, the number of microorganisms, you should have 1,000 times reduction. Okay. Then by 7 days, you should not observe any microorganisms. Sawa. Again, with the fungi, okay, you want a scenario whereby with the At 7 days, remember fungi multiply at a slower rate, okay? At 7 days, you have a 2 log reduction, okay? And then now here at 14 days, okay, you should not be seeing any microorganisms growing, okay? So I hope that is clear, okay? Okay. So when remember you have okay, let's go back to this slide. So you have, assuming you have a 20 ml product, you added uh, you added your inoculant, okay? Because this product is preserved. What do you want to see? You want to see, I'm answering the question that is on the chat. What does it mean when you say withdraw? You have 20 ml product, you add your inoculum to it, okay? Remember we said we are using these microorganisms, okay? These are the microorganisms we are using, okay? And we are going to add them to our product that contains preservative, okay? Expectation is that because the product contains preservative, these microorganisms should actually be killed. They should not multiply in the product, okay? But how are we able to tell that these microorganisms that we added to the product actually died? We cannot be able to tell that unless we can actually plate it, okay? We pick a sample from the product, okay, and put it on growth media, okay, and then wait to see whether we will see any growth, okay? And how are we doing that? We are going into that sample, withdraw an amount after 6 hours to see at 6 hours, do we still have any viable microorganisms in the product, okay? At 24 hours, do we still have any microorganisms in the product, okay? At 7 days, at 14 days, at 28 days, do we still have any microorganisms in that product, okay? And this is what we are saying, okay? That when you withdraw that product, part of that product, and plate it on growth media, at 6 hours, you should be able to see a 2 times log reduction, okay? At 3, you should be, at 24 hours, you should be able to see a 3 times log reduction, okay? And uh, implication is that with with this reduction in numbers, okay, by the time you're getting to 14 days, because remember you started with 10 to the power of 5, okay? If a 2 times, a 2 log reduction is giving you 99% in the reduction in the number of microorganisms, okay? Then as you go, you're reducing. By the time you're getting to 14 days, you will not have any observable microorganisms. So that now when you plate, you're not able to you're not able to observe microorganisms. Is that answering your question? Okay, then we have another question. Why are we neutralizing the preservative in the method, yet we are investigating its effectiveness? Now, remember, we added the preservative. If we go back to this again, just where we were, we are adding preservative to these containers, okay? We want to see uh, when this basically we want to see, is this preservative effective against these microorganism, okay? So that if it is effective, we will be able to see based on this reduction, okay? If at 6 hours, we are only able to find one, because if we are getting a 2-log reduction, it means that we have 99% having been destroyed. If we do a 1-log reduction, it means 90% have been destroyed, we only have 10%, and all that, okay? So what we want to see is whether this preservative has worked and been able to reduce the microorganism, okay? So we come at 6 hours. Remember, we added the amount of microorganisms we added was 1 times 10 to the power of 5, okay? So that's the amount we added. When we come and check, if we find 10 to the power of 5, we know that this or if we find a higher number, then we know that these microorganisms have not been stopped from growing. They are still growing, okay? But if we find a reduction, it means that the number is reducing, okay? But remember, for you to be able to count the number that is remaining in solution, okay? Because there's some that have been killed, but there's an amount that is remaining in solution. What do you do? How do you count the amount remaining in solution? You take them, you place them on a plate, you remove the preservative, okay? Because then you're able to test these are the number that is remaining in solution. And with that, as you're doing it consecutively at 6 hours, 24 hours, 7 days, 14 days, you will be able to see this reduction until at some point, 7 days, if you observe no growth, you can comfortably say that within that product, all the microorganisms were killed. Does that answer your question? But if we are not able to neutralize, okay, if we don't neutralize, okay, then it's possible that as much as we have plated, there could be a microorganism that is alive. But remember the colony forming units. We said that when you plate on a media, you will only be able to, you get one cell that divides and gives you a colony, okay? But without it dividing, you will not be able to see the colony. So you may assume that there is no growth, when in the real sense there is actually growth. It's just that the preservative is hindering the multiplication of that cell. So you neutralize this preservative to allow any microorganisms that are remaining to be able to actually grow, and you're able to tell the number that is remaining. So I hope that is clear. Okay. So again, for year preparations, remember we divided our products into categories, okay? And we said that with the bacteria, or rather with the second category, again, you will check after 2 days, after 7 days, 14 days, 28 days, okay? And within the 2 days, there should be a 2-log reduction, 3-log reduction. By 14 days, you should see nothing, okay? And then again, think of oral preparations, okay? Again, these are checked at 14 days, 28 days, okay? At 14 days, you should have a 3-log reduction. At 28 days, no increase in the number of viable microorganisms. Okay. So when do you conduct a preservative effectiveness test? It is important to determine if the preservative chosen for a product is compatible with the formulation soon after manufacture. Okay, because remember, you may actually add a preservative to a product, okay, and then you didn't know that the preservative is actually interacting with your product, okay, so it does not have free preservative. So you test it to see whether your full formulated product is actually able to prevent growth of microorganisms. So it determines if the preservative chosen is compatible. Because remember, if it is not compatible, as much as you've added the correct amount, you will still observe growth because free preservative is not enough in the product. Again, it may also be helpful to perform a second challenge test within 2 to 3 months of manufacture or as appropriate to the intended shelf life as part of your stability testing regimen. Okay, so this will aid in ensuring that as the product ages, the preservative system is not breaking down and becoming less effective. So we've talked about after formulation. Immediately after formulation, you want to see whether the preservative is compatible. But again, as you're storing the product, remember when during your GMP class, we said or even during formulation, you said when you formulate your product after production, you leave samples within the pharmaceutical industry and they are kept at the required conditions, okay? These products will be tested for stability. But apart from that, you should also be able to test the preservative system, okay, to ensure that the preservative system is also maintained throughout the shelf life of this product, okay. Again, it is also necessary to re-evaluate preservative effectiveness in your product whenever the formulation and associated manufacturing process or product packaging changes occur. Okay. Again, remember we said it's possible for you to have a very good product, but the packaging system you place the product in is not good enough. Okay, it is interacting with the product. Okay, so because of that product packaging system, you test just to be able to prove that the preservative is effective for the full duration. Okay, because you may change a package and then you realize that the new package you're using is actually interacting with your pharmaceutical product. Okay. Any questions? Okay, so if there are no questions, we will look at pharmaceutical application of, or rather industrial application of microorganisms. So this is industrial. Remember, okay, what shelf life aspect is the neutralization of the preservative simulating? Is it assuming there might be complete neutralization of preservative by physical-chemical factors and trying to account for bacterial? Okay, let's see. So last week, if you were in class last week, one of the things we mentioned this, okay? And we said that one of the challenges with the pharmaceutical products usually we tend, not pharmaceutical products, with the part of our class, okay, or our curriculum or syllabus. Generally, we have concentrated on the API with regards to stability, okay? We mentioned, I believe it was in this class that we mentioned that, okay? And we said most of the time when we look at stability of a pharmaceutical product, it is based mainly on the API, or active pharmaceutical ingredient. But remember, your pharmaceutical product is not only the API. Your the reason we are referring to it as a pharmaceutical product is because it is a balanced system. It is a balanced product containing the API, the vehicle, the stabilizers, whether you're stabilizing pH or stabilizing ionic concentration, all those aspects are concerned. And then you also have stability with regards to microbiological stability. Okay, so all these aspects have to be taken care of. It's not only the chemical stability of the API. We also have physical stability. For instance, if you're thinking of a suspension, okay, when you think about a suspension, and when I tell you to talk about stability of a suspension, there are two aspects. You could have stability of the active ingredient, whereby with time it is degrading, and then you could have stability of the physical product, in the sense that it is a suspension. And what are some of the instabilities of a suspension? We have sedimentation, things like that. Okay, so when you talk about stability, there are very many aspects that will come to mind. Okay, so that those are some of the aspects that you will think about. But we may not always, because I mean, with the scope of what we need to cover, it may take us forever just to be able to finish one aspect. Okay, so for the rest of this, as we said, you're given the power to read. Okay, so you will encounter most of this when you get into practice. But now back to this question that Brian is asking, okay? The shelf life aspect, okay? That the neutralization of the preservative is simulating. Remember, we are talking about stability. With shelf life, what comes to mind? Stability. Stability in what sense? Stability chemically of the API, stability physically of the pharmaceutical product, whether it's an emulsion that is going to remain stable and not cream and separate out into two layers of liquid, or microbiological stability, whereby you're looking at a pharmaceutical product getting microorganisms. Okay, so for instance, if you remember our dispensing class, okay, we talked about eye drops. Okay, what did we say about eye drops when they are opened? What did we say about their shelf life? And so, do you remember what we said about the shelf life
Hello,
of eye drops?
hello.
Yes, hello.
For eye drops, when they are open, the shelf life decreases. Like you'll find you're told, use this one for once you open, it should not exceed this number of days. And you're told maybe to keep at a given temperature once you open them.
Yes. Okay. So now going back to Brian's question. Okay. At the point when you're being told use your eye drops for 1 month post opening and not beyond, what is your manufacturer telling you? It's not that your API will actually uh, Yes, the shelf life decreases to 4 weeks. Okay, when you open an eye drop, shelf life reduces to 4 weeks. But remember, if you look at that eye drop, it has an expiry date. If you don't open it, that shelf life could be 2 years, could be 3 years. But once you open it like this, it reduces to 4 weeks. Why is that? It's because the manufacturer can only assure you of microbiological stability for 4 weeks. Beyond that, they can't assure microbiological stability because the preservative, as much as preservative has been added into that product, okay, it's possible that beyond 4 weeks, they will not be able to assure you that the product is still safe for use. Okay. So is it assuming there might be complete neutralization of preservative by physical chemical factors and trying to account for bacterial contamination at that point? Okay, does that answer your question, Brian? Okay. So again, remember we said all these aspects. When you get into practice, all those are all the things that now you need to tie together. Okay. Not only API stability. Think about API stability. Think about product stability. Think about pH stability. Okay. pH might change with time. How will that affect stability of your product? Think about ionic stability. How will that affect, uh, you know, if you're dealing with the things like, remember things like proteins. Proteins will be destabilized by ionic, uh, concentrations. So again, those are things you need to think about. With time, how is the ionic strength of your product going to affect stability of your protein? So those are some of the aspects that you need to look at. Okay. If there are no other questions, I want us to get into industrial application of microorganisms. Okay, and these are basically aspects that you know. Okay, it's just that for a few things here and there, we are going to look at them more in depth. Okay, so industrial application of microorganisms. Mainly, this is through a process we refer to as fermentation. Okay. Industrial manufacture of most antibiotics is based on the large-scale production of microorganisms. The microorganisms convert raw materials into antibiotics, a process referred to as fermentation. Wine and beer making also involve the fermentation process. Traditional fermentations are biological processes occurring in the absence of air or oxygen, although the term is now commonly applied to any large-scale cultivation of microorganisms, whether aerobic with oxygen or anaerobic without oxygen. So how have some of the microorganisms been applied? Production of antibiotics. You guys are aware of penicillin, for example. Okay. Production of vaccines. Okay. Uh, in digestion of food in human beings and fight against disease-causing microbes as food supplements, for instance, spirulina. Okay. So these microorganisms have actually found a lot of use. The list, of course, is not exhaustive. Remember, we had a longer list, okay, when we were looking at microorganisms earlier in this unit, okay? You can look at that. Microorganisms have found a lot of use in pharmaceuticals, okay? So let's look at fermentation. After production by fermentation, antibiotics are recovered, concentrated, and purified by a series of downstream processing stages. For semi-synthetic antibiotics, there will then be chemical conversion stages to produce the bulk antibiotic or active pharmaceutical ingredient. The bulk antibiotic or API is formulated into the required dosage forms, such as tablets, vials for injection, solutions, ointments, and so on. Stages up to bulk API are commonly termed primary manufacture. Stages from API to the formulated product are referred to as secondary manufacture. So why do we use microorganisms in the production of pharmaceuticals? One, through genetic engineering, genes coding for important proteins can be introduced into bacteria, which can then synthesize vast amounts of proteins from the recombinant genes. Okay, so and this you have probably talked about even in your biotechnology. Okay, bacteria cells are cheap, okay, to grow on large scale in fermenters. Therefore, the cost of the drug is greatly reduced and the availability is increased. If you compare this, for instance, to insulin, initially when insulin used to be produced from animals. Okay, what would happen is the cost of insulin was very high. Okay, the cost of insulin was very high, so it was actually becoming very expensive for the patients. Okay, because you needed to remove the insulin from the animals. Okay, but now with the introduction of this uh, use of microorganisms, they are cheap. So that means even the cost that is being passed to the patient is actually quite low. Okay, so that's why we are saying that the cost of production actually reduces with the use of microorganisms. Okay, so it's important for you to note that. Okay, next we have microorganisms are useful in achieving specific modifications. Okay, so when you think about complex drug molecules, one of the things that you will appreciate, especially when you look at production of drugs through synthesis, okay? One of the things you'll appreciate is that synthesis of simple molecules can be very straightforward, okay? But when you're looking at complex drug molecules, okay, whereby you need to achieve stereospecificity, and if you don't, then the compound is not active. It means that it can become quite complex. Okay, it may not be possible to achieve that kind of specificity. Okay, so what has been found is that microorganisms are actually able to achieve this very specific modifications of complex drug molecules, such as steroids, especially where synthetic routes are difficult and expensive to carry out. Okay, microorganisms are able to carry out stereospecific and regiospecific modifications, which would be difficult and expensive to carry out synthetically. Okay, remember from your biochemistry, hopefully you are told that receptors can be very stereospecific, okay, so that you may, if you do not produce a stereospecific compound, it may actually fail to bind to a receptor because of that stereochemistry, the wrong stereochemistry, okay. And then fermentation is useful, especially in the production of compounds which are solely produced by microorganisms, such as antibiotics. Okay. So there are some compounds that cannot be produced any other way. Okay. Or even if you try to produce them, the cost would be too high. Okay. So this fermentation becomes quite useful because then it can be done by microorganisms. They can also be used to generate starting materials in semi-synthetic production of API. So again, one of the things you'll realize is that for some of these antibiotics, usually you generate the compound using microorganisms, and then you use that compound as a raw material now to generate other classes of antibiotics, okay, which now gives you a semi-synthetic process, okay, whereby you first generate the raw material, then you use the synthetic process to modify it and give you a better acting compound, okay. So the immunogenicity of pharmaceutical products produced by microorganisms is very low since they resemble the natural human proteins as much as possible. This is because the genes responsible for the natural protein are used in the production. Again, going back to your biotechnology, okay? When you think about production of insulin, initially when insulin was being used from the hog or the cow, it's similar, yes. It's able to give you the effect you want, but the problem was this was a foreign protein, okay? It was still a foreign protein. Therefore, you are not able, it's possible for you to get immunogenic reactions in human beings, okay? But with the use of microorganisms, you basically pick the gene that is responsible for the natural insulin in human beings. You insert it in microorganisms, and then what do the microorganisms do? They start generating the human protein, okay, the human insulin, so that now human beings are not reacting to this protein the way they were reacting to the one that was produced from the cow and the pig, okay. So again, it's something to note, okay, that that helps. If you use microorganisms, you're able to actually come up with a protein that is less immunogenic. If it is less immunogenic, it means that human beings will actually not be able to react to it, okay? There will be less reactions to that product, and therefore it will be more biocompatible. Any questions? So if there are no questions, we will stop here for today. Next week, we will look at the use of microorganisms in the industrial production of benzyl penicillin. If you're reading ahead, you can go ahead and look at that. We will basically look at that process, okay, so that we are able to appreciate what goes on. Because one of the things that you'll appreciate is that uh, these are microorganisms, okay? It's basically what are the key things what are the key things you need to consider when handling them, okay? Those are some of the things that I want you to be able to grasp, okay? Things to do with the conditions, okay? And how do you handle the process? How do you ensure that you get more of the product that you want, and not just microorganism proliferating indefinitely, okay? So that is what we will be looking at, okay? So we will stop there for today. I believe we still have, okay. So we look at that next week. We still have to look at bacterial resistance to antibiotics. And then after that, we will look at antibiotic and disinfection policies. That will be our last topic, okay? So we still have about, we need about 2 or roughly 3 sessions, okay? Because hopefully we will finish this industrial application within 1 session. Then we can look at bacterial resistance within another session and antibiotic and disinfection policies within another section. Okay, so if there are no questions, we will stop there for today. Have a good afternoon. I will see you next time. Thank you.